Okay, so for today's lesson, we are going to be continuing talking about excited state and ground state electrons. We're going to be learning about something called a line spectra or emission spectra of an atom. Okay, so today we're going to be analyzing the line spectra or emission spectra of an atom in excited state. We're going to be able to do three things. We're going to be able to explain how these emission spectra are formed. We're going to be able to identify an unknown substance using an emission spectra. And we're going to be able to explain how an atom releases light in terms of ground state and excited state electrons. So getting started with what is an emission spectra. Okay, so this is very important, especially what I have in bold. Okay, so we've discussed that an atom is in ground state, right? So I'm going to draw like a very not professional diagram down here so we can visualize it. Okay, so we have an electron in ground state. So let's just imagine this little red circle is the electron and that line represents ground state. Okay? Now, when the atom becomes excited, one of those electrons gains energy, right? So energy increases and goes up to excited state. Okay? So when it goes from ground state to excited state, energy increases. So the electron jumps up to a higher orbit, okay, because it increases energy, it became excited. Now, it won't stay there forever. Whatever goes up has to come down, right? So once that atom in excited state has too much energy, it now has to come back down to ground state. So now, from excited state, it won't stay up there forever. Okay, again, it'll jump up, it'll stay there for a period of time, and then it has to eventually come back down to ground state. So now, it will come down, back down to ground state. And in that process, it will lose energy. Okay? So going up, it gains energy. I'm going to put gains in parentheses over here. So going up from ground state to excited state, it gains energy. Energy is increasing. It'll stay up there for a little bit, and when it comes back down, it loses or releases energy. Okay, now, energy is never created or destroyed, so that energy does not just disappear. So what happens is, on its way back down from excited state to ground state, it will release or emit. That word emit means to release or lose energy in the form of light, creating a spectra. Okay, so again, energy is never created or destroyed. So that energy that it's losing or emitting as that electron's coming back down has to be released somehow. So what happens is it is released in the form of light. So that energy is released, and we call it light or a photon. Okay, so again, when that electron becomes excited, it gains energy, it goes up to excited state. It'll chill there for a little, and then eventually it comes back down. On its way back down from excited state to ground state, it will release or emit energy in the form of light. Okay, we call it a photon. Photon is a particle of light. Now, all light corresponds to something called a spectra. Okay, and each element has its own spectra, meaning when each element is excited, okay, and it's coming back down, it releases a different form of light, okay? And an emission spectra, what happens is it creates this pattern of lines, and they all correspond to a certain wavelength. So I want to show you something. Okay, so here is the periodic table of elements. So I'm going to show you a few things. Let's look at carbon. This is the line spectra, the pattern of lines that carbon makes when it goes from excited state back down to ground state. So this is the pattern of lines it creates that corresponds to that energy it's releasing as a photon, okay? So this corresponds to a certain color. Okay, every element, when excited, creates a different color. Okay, so what we can do, and I'm going to show you a video, is certain elements you can put in a flame, and that flame will turn a color that corresponds to its pattern of lines. So that's carbon. Let's look at lithium. Okay, here's the pattern for lithium. You can see it's a different pattern from carbon. Okay, now you can see its thickest line is in red. So when we burn lithium, it burns like a reddish magenta color. Okay, because its line patterns correspond most with the reddish color. Let's look at oxygen. Okay, we can see oxygen has a lot of lines present in that orange, yellow, red space. So when we burn oxygen, and it also has its own line pattern, its own line spectra, when we burn oxygen, it'll burn in like an orange, reddish, yellow color. Okay, let's look at one more. Let's look at copper. Okay, copper has some prominent lines in the blue-purple. Again, every element has its own line spectra. So this is carbon's line spectra or line patterns. And it usually burns, it has the most prominent in the green range. The most green lines, they're thick, they're there. So copper burns like a bright green when you put it in a flame. Okay, so before we get on to how we use the line spectra, I want to show you two videos about what it means when we excite electrons and how we get these emission spectra. Okay, so I'm going to pull up two videos. Just give me 1 second.
If a sample of hydrogen gas is heated, it gives off light. When you view this light through a prism, you'll see an emission spectrum consisting of bright lines at specific frequencies.
Okay, so again, hydrogen's being heated up, meaning it's gaining energy, it's being exposed to energy. Those electrons became excited, and now that pink color we're seeing, that's when those electrons are moving from excited state back down to ground state. That's why those pink arrows are pointing out, because it's releasing energy. And that pink color corresponds to a certain line spectra, a certain line pattern.
Because the spectral lines come at definite intervals, this suggests that specific energy levels exist in the atom. A cross-section of an atom shows the energy levels similar to the rungs of a ladder. When energized, the electrons move temporarily to higher energy levels. As the electrons fall back to lower energy levels, they lose energy in the form of light, which produces the characteristic spectrum of the element. Because we know that the emission spectrum for each element is different, we also know that the distances between energy levels must be different for every element.
Okay, so again, I'm just going to go back to that last part. So every element has a different line spectra, okay? So that gives us proof that every element, its orbits or its shells around the nucleus are at different distances. So depending on how far that electron has to travel, when it's moving up in orbit and then coming back down, that corresponds to a different line pattern. So that is why every element has its different line pattern, because every element's shells around the nucleus are at different distances, okay? And that distance that an electron has to travel when it's coming back down and releasing energy in the form of light corresponds to a different line pattern. Okay, one more on those flame colors.
When some elements are placed in the heat of a flame, they emit colors that are characteristic of that element. Common elements with flame tests include copper, which burns with a green flame, lithium, which burns with a red flame, calcium, which burns with an orange-red flame, strontium, which burns with a red flame, and sodium, which burns with an orange flame.
So again, those colors that are burning, that corresponds to that element's line pattern. And those colors are formed when that atom's electrons move from excited back down to ground state. Okay, so it happens within milliseconds. The second you put that element in the flame, it gets excited because you're giving it energy and those electrons move up. As soon as you see the color, that's when those electrons are moving from excited state back down to ground state and releasing energy in the form of light. Now, how we use these line spectra is we use them to identify elements of an unknown compound. Okay, so we have to try and match them. We have to line up the lines to identify elements in a mixture. Okay, and I'm going to show you how we do this. We're going to do a couple practice problems. So first, let's do guided practice problem number 1, which is just taking us back to ground state and excited state electron configuration. So which electron configuration represents an atom of aluminum in excited state? So first of all, aluminum has a ground state electron configuration of 283. That's its ground state. Okay, it has a total of 13 electrons. So we need to determine which one is the excited state electron configuration. So first of all, we can take out C and D because those are ground state electron configurations. And we know that because they're following the 2-8-18 rule. So now we have to look at A and B and determine which both look like excited state configurations because that second shell is only filled up to 7. So that is not following the 2-8-18 rule. And we need to see which one would be the excited state for aluminum. Now, you might kind of see it already that one of the electrons left the second shell and went into the third shell. So the second shell went down 1 and the third shell went up 1. Another way you could identify which one is aluminum is by counting up the total number of electrons. So aluminum has 13 electrons. So for A, 2 plus 7 plus 4 is 13. So it would be A. Okay? All right. Now we're going to look at our line spectra. So here's an example of a bright line spectra. Okay, and it's telling us we have given the bright line spectra of 3 elements and the spectra of a mixture formed from at least 2 of these elements. So what we need to do, we have to figure out of these 3 elements, which 2 are located in the mixture. So we don't know what the mixture is and we need to figure it out. So the way we do this is we start with the first element. Now, every line that is in the element pattern has to be present in the mixture pattern. Now, because it's a mixture, there's going to be other lines there. But if every line in that element is present in the mixture pattern, then that element is present in the mixture. So for example, let's look at element D. We're going to look at this first line, and I'm going to highlight them. We can see that line is present in the mixture. It lines up. It matches. This line also matches. Okay? This line also matches. This line is there. This line is there. And this line is there. So, all of the lines in element D are present in the mixture. Now you can see we didn't highlight every line in the mixture, but that's because there's something else in there. So that's okay. What's important is that every single line in element D is present in the mixture. So element D is in this mixture. Okay? Now let's see element E. And I'm going to put it in a different color. So element E, this line we could see is there. This line matches up. This line matches up. And this line also matches up. So every line from element E is present in the mixture. Okay? So element E is also in the mixture. So right off the bat, we can see, because it's only 2 elements they're telling us that are present in the mixture, element D and element E are present in the mixture. Okay, so that would be our answer, choice 1, element E and D only. Okay, and you can also see that the line pattern for the mixture is a combination of the 2 line patterns for element D and E. So if we superimposed element E over element D, we would get the mixture pattern. Now, let me show you what it looks like when an element is not present in the mixture. So for example, starting with element G, this line here, it's nowhere to be found in the mixture. There is nothing here. So right away, element G is not present in the mixture. All it takes is one line to not be there. There can be other lines that match up, but all you need is one line to not be there, and that element is not present in the mixture. Okay? Now, usually these will be given to you in black and white. When they're in color, it's obviously a lot easier because it's a lot easier to match it up. So if we look at the top, there is the unknown, and we have to try and figure out what this unknown element is. Okay, so if we start with beryllium and compare it with the unknown, we can already see that, hold on, let me figure out what's the best color to use here. I'll just do it in red. We can already see that beryllium has this purple line, and the unknown does not have that purple line. Therefore, this is not beryllium. Copper. Copper has these 3 green lines. The unknown does not have those 3 green lines. Manganese. Manganese, this first purple line, is not present in the unknown element, so it's not manganese. Strontium. Strontium has this blue line. That blue line is there. It has these 3 lighter blue lines. Those 3 lines are there. It has this orange line. That's there. This red line. That's there. And this last little orangey red line at the end, that is there. So this is strontium. Okay? And just to reference, if you look at titanium, it starts with this like teal colored line. That's not present in the unknown mixture, so it can't be titanium either. Okay? So that's how we figure out what unknown elements or unknown substances are present in a sample. Okay?